The biological and geological future of the Earth can be extrapolated based upon the estimated effects of several long-term influences. These include the chemistry at the Earth's surface, the rate of cooling of the planet's interior, the gravitational interactions with other objects in the solar system, and a steady increase in the Sun's luminosity. An uncertain factor in this extrapolation is the ongoing influence of technology introduced by humans, such as climate engineering, which could cause significant changes to the planet. The current Holocene extinction is being caused by technology, and the effects may last for up to 5 million years. In turn, technology may result in the extinction of humanity, leaving the planet to gradually return to a slower evolutionary pace, resulting solely from long-term natural processes. Over time intervals of hundreds of millions of years, random celestial events pose a global risk to the biosphere, which can result in mass extinctions. These include impacts by comets or asteroids with diameters of 5 to 10 kilometers or more, and the possibility of a massive stellar explosion, called a supernova, within a 100 light-year radius of the Sun, called a near-Earth supernova. Other large-scale geological events are more predictable, if the long-term effects of global warming are disregarded. Milankovitch theory predicts that the planet will continue to undergo glacial periods at least until the Quaternary glaciation comes to an end. These periods are caused by eccentricity, axial tilt, and precession of the Earth's orbit. As part of the ongoing supercontinent cycle, plate tectonics will probably result in a supercontinent in 250 to 350 million years. Sometime in the next 1.5–4.5 billion years, the axial tilt of the Earth may begin to undergo chaotic variations, with changes in the axial tilt of up to 90 degrees. During the next 4 billion years, the luminosity of the Sun will steadily increase, resulting in a rise in the solar radiation reaching the Earth. This will cause a higher rate of weathering of silicate minerals, which will cause a decrease in the level of carbon dioxide in the atmosphere. In about 600 million years, the level of CO2 will fall below the level needed to sustain C3 carbon fixation photosynthesis used by trees. Some plants use the C4 carbon fixation method, allowing them to persist at CO2 concentrations as low as 10 parts per million. However, the long-term trend is for plant life to die off altogether. The extinction of plants will be the demise of almost all animal life, since plants are the base of the food chain on Earth. In about 1.1 billion years, the solar luminosity will be 10% higher than at present. This will cause the atmosphere to become a moist greenhouse, resulting in a runaway evaporation of the oceans. As a likely consequence, plate tectonics will come to an end, and with them the entire carbon cycle. Following this event, the planet's magnetic dynamo may come to an end, causing the magnetosphere to decay and leading to an accelerated loss of volatiles from the outer atmosphere. 4 billion years from now, the increase in the Earth's surface temperature will cause a runaway greenhouse effect. By that point, most if not all the life on the surface will be extinct. The most probable fate of the planet is absorption by the Sun in about 7.5 billion years, after the star has entered the red giant phase and expanded to cross the planet's current orbit. Human influence. Humans now play a key role in the biosphere, with the large human population dominating many of Earth's ecosystems. This has resulted in a widespread, ongoing mass extinction of other species during the present geological epoch, now known as the Holocene extinction. The large-scale loss of species caused by human influence since the 1950s has been called the biotic crisis, with an estimated 10% of the total species lost as of 2007. At current rates, about 30% of species are at risk of extinction in the next 100 years. The Holocene extinction event is the result of habitat destruction, the widespread distribution of invasive species, hunting, and climate change. In the present day, human activity has had a significant impact on the surface of the planet. More than a third of the land surface has been modified by human actions, and humans use about 20% of global primary production. The concentration of carbon dioxide in the atmosphere has increased by close to 30% since the start of the Industrial Revolution. The consequences of a persistent biotic crisis have been predicted to last for at least 5 million years. It could result in a decline in biodiversity and homogenization of biotas, accompanied by a proliferation of species that are opportunistic, such as pests and weeds. Novel species may also emerge, in particular taxa that prosper in human-dominated ecosystems may rapidly diversify into many new species. Microbes are likely to benefit from the increase in nutrient-enriched environmental niches. No new species of existing large vertebrates are likely to arise, and food chains will probably be shortened. There are multiple scenarios for known risks that can have a global impact on the planet. From the perspective of humanity, these can be subdivided into survivable risks and terminal risks. Risks that humanity posed to itself include climate change, the misuse of nanotechnology, a nuclear holocaust, warfare with a programmed superintelligence, a genetically engineered disease, or a disaster caused by a physics experiment. Similarly, several natural events may pose a doomsday threat, including a highly virulent disease, the impact of an asteroid or comet, runaway greenhouse effect, and resource depletion. There may also be the possibility of an infestation by an extraterrestrial life form. The actual odds of these scenarios are difficult if not impossible to deduce. Should the human race become extinct, then the various features assembled by humanity will begin to decay. The largest structures have an estimated decay half-life of about 1,000 years. The last surviving structures would most likely be open-pit mines, large landfills, major highways, wide canal cuts, and earth-fill flank dams. A few massive stone monuments like the pyramids at the Giza necropolis or the sculptures at Mount Rushmore may still survive in some form after a million years. Random events. As the Sun orbits the Milky Way, wandering stars may approach close enough to have a disruptive influence on the solar system. A close stellar encounter may cause a significant reduction in the perihelion distances of comets in the Oort cloud, a spherical region of icy bodies orbiting within half a light-year of the Sun. Such an encounter can trigger a 40-fold increase in the number of comets reaching the inner solar system. Impacts from these comets can trigger a mass extinction of life on Earth. These disruptive encounters occur at an average of once every 45 million years. The mean time for the Sun to collide with another star in the solar neighborhood is approximately 3 times 10^13 years, which is much longer than the estimated age of the Milky Way galaxy, at 1 to 2 times 10^10 years. This can be taken as an indication of the low likelihood of such an event occurring during the lifetime of the Earth. The energy release from the impact of an asteroid or comet with a diameter of 5 to 10 kilometers or larger is sufficient to create a global environmental disaster and cause a statistically significant increase in the number of species extinctions. Among the deleterious effects resulting from a major impact event is a cloud of fine dust ejecta blanketing the planet, which lowers land temperatures by about 15 degrees Celsius within a week and halts photosynthesis for several months. The mean time between major impacts is estimated to be at least 100 million years. During the last 540 million years, simulations demonstrated that such an impact rate is sufficient to cause 5 to 6 mass extinctions and 20 to 30 lower severity events. This matches the geologic record of significant extinctions during the Phanerozoic Eon. Such events can be expected to continue into the future. A supernova is a cataclysmic explosion of a star within the Milky Way galaxy. Supernova explosions occur on average once every 40 years. During the history of the Earth, multiple such events have likely occurred within a distance of 100 light-years. Explosions inside this distance can contaminate the planet with radioisotopes and possibly impact the biosphere. Gamma rays emitted by a supernova react with nitrogen in the atmosphere, producing nitrous oxides. These molecules cause a depletion of the ozone layer that protects the surface from ultraviolet radiation from the sun. An increase in UVB radiation of only 10 to 30% is sufficient to cause a significant impact to life, particularly to the phytoplankton that form the base of the oceanic food chain. A supernova explosion at a distance of 26 light-years will reduce the ozone column density by half. On average, a supernova explosion occurs within 32 light-years once every few hundred million years, resulting in a depletion of the ozone layer lasting several centuries. Over the next 2 billion years, there will be about 20 supernova explosions and 1 gamma-ray burst that will have a significant impact on the planet's biosphere. The incremental effect of gravitational perturbations between the planets causes the inner solar system as a whole to behave chaotically over long time periods. This does not significantly affect the stability of the solar system over intervals of a few million years or less. But over billions of years the orbits of the planets become unpredictable. Computer simulations of the solar system's evolution over the next 5 billion years suggest that there is a small chance that a collision could occur between Earth and either Mercury, Venus, or Mars. During the same interval, the odds that the Earth will be scattered out of the solar system by a passing star are on the order of 1 part in 105. In such a scenario, the oceans would freeze solid within several million years, leaving only a few pockets of liquid water about 14 kilometers underground. There is a remote chance that the Earth will instead be captured by a passing binary star system, allowing the planet's biosphere to remain intact. The odds of this happening are about 1 chance in 3 million. Orbit and rotation. The gravitational perturbations of the other planets in the solar system combine to modify the orbit of the Earth and the orientation of its spin axis. These changes can influence the planetary climate. Glaciation. Historically, there have been cyclical ice ages in which glacial sheets periodically covered the higher latitudes of the continents. Ice ages may occur because of changes in ocean circulation and continentality induced by plate tectonics. The Milankovitch theory predicts that glacial periods occur during ice ages because of astronomical factors in combination with climate feedback mechanisms. The primary astronomical drivers are a higher than normal orbital eccentricity, a low axial tilt, and the alignment of summer solstice with the aphelion. Each of these effects occur cyclically. For example, the eccentricity changes over time cycles of about 100,000 and 400,000 years, with the value ranging from less than 0.01 up to 0.05. This is equivalent to a change of the semi-mean or axis of the planet's orbit from 99.95% of the semi-major axis to 99.88%, respectively. The Earth is passing through an ice age known as the Quaternary glaciation, and is presently in the Holocene interglacial period. This period would normally be expected to end in about 25,000 years. However, the increased rate of carbon dioxide release into the atmosphere by humans may delay the onset of the next glacial period until at least 50,000–130,000 years from now. On the other hand, a global warming period of finite duration will probably only impact the glacial period for about 5,000 years. Thus, a brief period of global warming induced through a few centuries' worth of greenhouse gas emission would only have a limited impact in the long term. Obliquity. The tidal acceleration of the Moon slows the rotation rate of the Earth and increases the Earth-Moon distance. Friction effects, between the core and mantle and between the atmosphere and surface, can dissipate the Earth's rotational energy. These combined effects are expected to increase the length of the day by more than 1.5 hours over the next 250 million years, and to increase the obliquity by about a half degree. The distance to the Moon will increase by about 1.5 Earth radii during the same period. Based on computer models, the presence of the Moon appears to stabilize the obliquity of the Earth, which may help the planet to avoid dramatic climate changes. This stability is achieved because the Moon increases the precession rate of the Earth's spin axis, thereby avoiding resonances between the precession of the spin and precession frequencies of the ascending node of the planet's orbit. However, as the semi-major axis of the Moon's orbit continues to increase in the future, this stabilizing effect will diminish. At some point, perturbation effects will probably cause chaotic variations in the obliquity of the Earth, and the axial tilt may change by angles as high as 90 degrees from the plane of the orbit. This is expected to occur within about 1.5–4.5 billion years, although the exact time is unknown. A high obliquity would probably result in dramatic changes in the climate and may destroy the planet's habitability. When the axial tilt of the Earth reaches 54 degrees, the equator will receive less radiation from the Sun than the poles. The planet could remain at an obliquity of 60 degrees to 90 degrees for periods as long as 10 million years.